Hello, in this video, I'll show you how to build the robot simulator. First, we set the settings for the screen, initializing the by game, and adding the screen settings. Here we have the loop for updating the screen with the color of the screen and updating the frames. So as you can see now, we have the screen ready for adding the environment. So for the environment, we have the maze. First, let's add random walls, as you can see, and then we have a function to draw these walls. So we have the height, we have the colors, and then this loop, we draw them for their coordinates using this function of drawing the walls in the bigram. So next, we initialize the maze and the main code, as you can see, and then we draw it in the for loop, and then as you can see, we have our worlds. So after we have implemented our environment, we need to implement our robot. So we create a new class with all the variables that needed for the robot, such as the coordinate, the x and y, the orientation variable, and the radius, the left and right wheels velocities, and the distance between these wheels, and the sensor, the range of the sensor, and 12, and we have 12 sensors, and then we need the font for displaying these variables on the screen. We have a draw function like the walls that we draw in the environment. So this function draws the robot. So as you can see, we have our robot with the white color. Next, we need to make it able to move. In order to update the position of the robot, we need to create a function called update, which is going to use the time step used in the main code for the clock. So we need to initialize the clock and we get the frames and the time steps for each updated move. So as you can see here, we are using the 60 frames per second. So before we start implementing the update function for the robot, we need to handle the user inputs for moving the robot. So as you can see here, we have the W for moving forward, the S for moving backward, and A and D will handle turning left or right. And as you can see, we are updating the velocity here, and the speed is 18 as we specify it here. So the update function contains two variables that we needed for updating the position, the average speed and the angular speed. The average speed calculate the average of the left and the right speeds of the wheels to get the robot's learning speed. And for the angular speed, which is the omega, it calculates the turning speed based on the difference between the left and the right speeds of the wheels and the wheels distance L. So for calculation of the movement, we have the dx and dy, which calculates how far the robot moves from the x and the y directions using its speed and the orientation, which is theta. And d theta is a variable that calculates how much the robot angle change based on its speed of turning, which is the omega. And then we have the position and the orientation update, which is the robot's new position. So new X and new Y is updated by adding the DX and DY that we have calculated before. And we have the theta, which is updated using the D theta, which updates the robot orientation. So as you can see, the robot can move now, but we have two problems. We need to handle the collision of the movements with the wall and also the face of the robot. In order to handle the collision with the walls, we add a boolean which checks if there is a walls or not. And now the robot will stop when facing a wall. Now let's have a face of the robot. We add a new color. In order to draw this line, we need to calculate the heading of the x and y, basically by multiplying the x coordinates by the cosine and multiplying the y by the sine, and then we can have a line. As you can see, now we have the direction of the face of the robot. Now let's show the text of the speeds on the screen. Now we can see the velocity of the left and right wheels. So last method that we need to implement is the sensors method. As you can see, the list input here is the wall. And then we need to calculate the angles for the 12 sensors, which are 30 degrees spaced apart, starting from the robot current angle, which is the theta here. And then we loop through all these angles in order to calculate the ray. So the ray starts from the edge of the robot, not from the center. So using the self radius, and the endpoint is calculated based on how far this sensor sees
the wall. So sensor line here is the line representing the sensor's path. And then we check for the interaction. So for each wall, it checks if the sensor array interact with, and if there is an interaction, it calculates the distance from the ray origin to the point. If multiple walls interacts, it only store the closest interaction. And then at the end, we store the results. And so last thing that we need to do is to draw these rays. So as we have done in get sensor method, we have the angles, and then we have the origin and the end points for each ray, and then the same calculation, we draw them. And as you can see, we can now see the sensors and the rays of the robot that interacted with the walls, and we can see the values and the distance that how much far the robot is from these walls. So in order to enhance the visualization of the maze, walls can be rendered with 3D shaded effect style. So we add a lighter shade to the top faces and a darker shade to the side faces to simulate the depth.